Good morning, good afternoon, everybody. I don't know, in the back rows, can you still hear me? Is that fine from noise? Okay. So it's my honor now to talk against what happens after lunch. So I hope you don't fall asleep. I will do my best. My advantage is I'm standing here, I can't fall asleep. And my name is Olaf Hagemann. I'm working for Extreme Networks. And the topic today is about software-defined networking. So what is the idea behind software-defined networking? What is all that open flow things people are talking about? And how does maybe software-defined networking change our networking world? That's what at least they are approaching. And we need to find out how that will come out in the next few years, maybe. So what are the drivers behind software-defined networking? What we see, and I see that myself, I see that in our company, I see that a lot of customer companies, the networks are getting more and more complicated. There's a bunch of new devices in there. There's wireless as preferred access technology, we have smartphones, we have tablets, we have users moving between places, we have users moving between different devices. So the challenge for the network is that when a user is connecting via his laptop and he's connecting via his smartphone and via his tablet, that he gets the same access in terms of performance and especially in terms of security as he is used to, not depending on which device he's using at the moment. So this is something, you know, when you look around here, what you have to do is you open your laptop, you're looking for an SSID, you connect to it, you have to type in a password, then I open a VPN to my company, then I start Outlook, then I have a connection between my mail server, and somewhat about 20 minutes later, I maybe have my email on my laptop. And it works, but it's not very comfortable. We want the network to be more intelligent, so that the network itself will find out, this is Olaf Hagemann being in Warsaw at the moment, and all the connections are making transparent, transparent in the behind the scenes, and I don't have to do any action to get access to my data. And also cloud computing is something that is driven by the mobility of users and devices. When you use different devices for your data, it doesn't make sense to have manual synchronization between different devices. So you need a central place where your data is stored, where you have access to, where the application is lying, and then you have direct access to that amount of data, to that container in the cloud, and it doesn't matter from which device you're trying to get access. And the issue with all these new technologies and services is that it makes our networks more complicated. And typical classical networks, as we build them today, they are rather static. So you have a bunch of devices, maybe a few hundred or even a few thousand devices, switches, routers, firewalls, stuff like that. And each of them has to be configured on its own. And the idea of software-defined networking is now to make this easier so that we have a single point of administration or maybe even a single point of automation so that you don't have to touch each and every single device in the network once you're trying to introduce a new application or to offer a new service to your customers or your users. So that has to be done automatically, which saves us a lot of time especially, and in these terms also a lot of money. So what's happening in the network world now is something that has taken place maybe in the early 80s, also in the computing device area. When you remember those days, we had computers, big computers, all were built by IBM. If you wanted to have a computer, you could go to IBM, buy a mainframe. It was specialized hardware. It was a specialized operating system. It was a closed system. it was proprietary, and it was expensive. What came out after this was that we have an open architecture in terms of the hardware. So the PC came out, and you have different operating systems you can run on each of your PCs. You don't go to, except you go to Apple, you have your own operating system on your own hardware. But all the others, you can use any PC in the world, and there's an open operating system on top, and what you have in between the applications, the operating system and the hardware, is open APIs, interfaces. They are well-defined interfaces you can rely on. So when you today write a code in, let's say, C++, you don't have to do it so that the x86 processor is able to understand it. You're using C++ commands, and in between you have a compiler. So there is an abstraction layer in between, and you rely on the possibilities of the compiler, that it is able to translate your high-level commands into a language that is understood by the processor. And if you go to another processor, you just need another compiler. But your program, your application, your highest abstraction level, it stays the same. You don't have to attach it or adapt it to your hardware. And that's the same what's going on, or what the idea is that should go on in the networking world. You have a picture, I was suddenly saw it's also here. Yeah. So we have specialized hardware, we have specialized operating systems, we have very complicated operating systems. Our operating system, Extreme XOS, right now has, I think, approximately 1.5 million lines of code. There's a bunch of features in there, there's a bunch of protocols in there, and it makes it rather complicated. Although it is a modular system and we try to build it as easy as we could, it's still a complicated piece of code. And the idea now is that also these operating systems can be decoupled from the hardware. So what you have is a merchant switching hardware you can buy at any of those switching vendors, and on top of it you put an open interface. And this interface can be understood or can be managed by different operating systems. So there's an operating system on top, an open operating system, which is able to run different sets of hardware, like you have it today with a PC. You go into a shop, you buy a PC, and you install the operating system you want to use. So the idea behind this is that once a day from now, maybe you go to a shop, you buy a switch, and you choose the operating system that is running the chip, the switch and the chip inside of it. That does work if the switch has an open interface, if there's an abstraction layer in between. And that's the main idea of what software-defined networking is. You have different layers in your network with standardized open interfaces in between, and each and every layer can be separate, and because of the standardized interfaces, they understand each other. So, in a nutshell, software-defined networking is all about abstraction. It's all about having defined layers, like we all know it from the protocols. We have a layer 2 network, we have a layer 3 network, and for example, IP doesn't care what kind of layer 2 technology is below. It just has an IP packet, and it knows I can hand it over to layer 2, and layer 2 takes care about that the packet is going from where I want it to be, where the destination is. And the same shall be made within the logic of the network, so that we have a kind of a network operating system that is able to control the complete hardware. Then we have a virtualization layer on top with a central network intelligence, and then we have the applications. And the applications can rely on the virtual layer of the network. So that makes it a little bit easier, because then when you are at a point like this, you just have to care about the applications. And if you want to enter a new application, it just has to be able to set the right, to send the right set of commands to the virtualization layer. The virtualization layer sends it to the network operating system, and the network operating system is sending it into the switches, and you're done. So what are the ideas behind it? There's a few. It came up first in a research environment at Stanford University, where they, for example, developed new routing protocols, and they wanted to test them. But the hardware they were using was not able to test the new routing protocol, because there was an operating system on it from the vendor who built the hardware. And so they couldn't test their routing protocol. So what they said is, if we remove the control plane from the switches and have it as a virtual instance, we can test our new routing protocols, even on existing hardware from different vendors. That was where it originally came from. But what some people found out in the meantime is that once we have an environment like this established, it could save us a lot of work, it could save us a lot of time, and at the end of the day, it could also save us a lot of money. And what you see here is that, you know, what happens in networks today is that there is no single place where you can have a complete overview of the status of the network. So when you look into your devices, into your switches, into your routers, and you want to know what status has my network, it needs your special knowledge. It needs your master kind of skill set. You look at routing tables, and then you think about what is the status of my network. So it's very complicated, and you need to know a lot of the protocols, the functionalities, the technology behind it. In an SDN network, this is no longer needed. You have a central place where you can have a look at the complete status of your network, and all the expert knowledge that was or is necessary today to run the network below is no longer needed, because you have a standardized open interface, and you can rely on that the layers below, they do their job. So what you tell them as a command from the top level, once you have set up this environment, you don't have to care about what's happening below in the machine room, if you want to do it like this. So maybe we have to find new jobs once software-defined networking is completely in place. I don't know. Maybe we can then deal with other things, make new inventions, and have new applications. So what's behind that is also, we want to reduce the cost of the networks, and we want to make them easier to run. So here you see another example of how such a layered network can look like. Below here, there's the switching hardware, what we have today as well. But we have an overlaying operating system, and then we have a kind of network virtualization layer on top, and on top of this we have the applications that come from the customer. And by the way, applications in the first step can be protocols like we knew them today. It can be an OSPF, it can be a BGP, it can be some kind of network access control that now is no longer the functionality of the hardware below, but is an application I put on top of the virtualization layer, which is on top of the network operating system. That's the idea behind it. And if you look at what we have today, we have networks like these. We have specialized hardware, and each and every switch has his own operating system, his own data plane. They are all the same. They all have a data plane and have a control plane. What happens in a switch is a packet is entering the ingress port. Then the switch looks at the packet and looks at the status of the data plane to decide on which port I have to forward this packet. That's every switch on this world is working like this. So there's a data plane. And on top of this, we have a control plane. And the control plane defines the status of the data plane. So the control plane is the one running the protocols like OSPF, BGP, ISIS, you name it. And then, according to what they found out by talking to other switches, they manipulate the status of the data plane. And what software-defined networking now is doing is that we are isolating, we are removing the control plane from the switches. So we have a centralized network operating system here, which is able to talk to each of these switches, the hardware switches, and is able to set the status of the data plane. And that's almost it. But the advantage is that here we can make centralized decisions. We have one single place where we can have a look at the complete status of the network. And we don't have to look into each and every router and switch to find out what is the status of my protocols, how many routes have been learned and stuff like that. So, on the other hand, that means this hardware down here can be much more simple than it is today. It just needs, and later on we're going to see an example, or we're going to talk about an example where one of the biggest internet companies, they have introduced a technology like that. It can be just a single chipset and the interface on top. In this terms, it's an open flow interface I put on a single, simple switching ASIC. And all the functionalities we have today, which make the codes in the switches so complicated, they are removed and are put into the centralized controller. And there is an open interface to the hardware, and we can have even different operating systems. So once we have that all defined in software, it's very easy to put different operating systems here in between, and we have that virtualization layer, and each of these operating systems, all of them can run at the same time using the same hardware, and due to the virtualization layer and the network operating system below, we have a standardized defined communication. So what does that give to us? It's a lot of flexibility. So imagine you want to have a new version of your network operating system, or you want to introduce a new application. With software-defined networking, you can easily take one of those network operating systems on an isolated server, and you can test it. And you can just put it into place, you test it on the isolated server, and you know upfront what this operating system or this new application is doing in your network once you introduce it. Or, as I said, if you have a new version of your operating system, you can run it in parallel. You can see if it works. If it doesn't work, you have a very easy way to roll back to your old system without the necessity to touch each and every switch or to reboot all those switches. Look at what operating systems updates do today in your networks. You have to bring them into all of your devices, and I say in 99%, you have to reboot the device. You have to reboot the complete network just to bring in a new version of your operating system. With software-defined networking, that's no longer needed. You just put another logical instance on top, and that's your new version of the operating system. So, that's how it could look like. We talked about this, and then now let's talk about how is that done with extreme networks. How are we doing it? What's our idea to be part of a software-defined network? So what we have down here is our hardware. By the way, those ones who don't know, what does extreme networks? I forgot that front. We are building Ethernet switches. That's it. So this is our hardware down here, and we have our operating system on top. Extreme XOS. It's a modular operating system based on hardened Linux kernels, and you have all these features and stuff running in single modules, which makes it much more stable and makes it much more easy to upgrade or to bring in certain new functionalities. Like we are going to talk about OpenFlow later on. When you want to do OpenFlow on a switch with XOS on it, on an extreme network switch, you just have to add another small module to the operating system. It's a few hundred K of code, and then you're done. That's the interface for OpenFlow, which is on top. And you can do that without to reboot the switch and all that stuff, so no problem. What we did from day one when we introduced XOS is that we had already open interfaces in there, like an XML interface. And we also have a software developers kit. So when you have your own application and you wanted to talk to the networking hardware, to the switches, there's an open interface. We can offer you the software developers kit for free, and you can integrate your own applications into the networking hardware. And we also already had a lot of possibilities to do automation via static or via dynamic scripts. So we can trigger on things like detecting devices, on network login events, on link down events, whatever you want. And then we can run automatic script and change the configuration of the switch. So the level of automation we already have is rather high, but it's not as high as software-defined networking is trying to bring it. So what we have on top then is management platforms. We have Ridgeline, which is our own network management software. And we have those two open interfaces. One is OpenFlow, the other one is OpenStack. I'm going to describe those later. And on top of this, we have the applications, user identity management, bring your own device, stuff like that, which is needed right now in the networks of our customers. So we put them on top of the, in this case, OpenFlow controller, and then it can access via OpenFlow the operating system of the switch, and this is configuring the hardware. What we do in this case is we have partnerships. When it comes to OpenFlow controllers, we support, right now we support 3 different versions. One is NEC, then we have all the Big Switch family, and Floodlight, which is the open source version of the Big Switch controller. You can easily go to the internet, just Floodlight, type it into Google, and you're going to find a link to download, and there's a virtual machine, and you have an OpenFlow controller on your laptop. It's a matter of minutes. So, what is OpenFlow? There's a lot of confusion about it when you listen to presentations and when you look around in the press. It's very often that people think OpenFlow is SDN. That's wrong. OpenFlow, and if there's one thing you have to take from today, from this presentation, OpenFlow is not SDN. OpenFlow can be a part of a software-defined network. OpenFlow is just a simple protocol. That's it. OpenFlow is a standardized protocol which can be used from a controller to talk to the hardware. And that's all. The idea above this, that's the software-defined network. And you also have to be careful when you look around what other vendors are telling you right now about software-defined network. There's a lot of marketing stuff, marketecture around it. So I know one or few vendors, they say, we have a network managing software. This network management software is managing our hardware. So this software is a piece of software, so we already have a software-defined network. Okay. But this is not what the real idea is behind software-defined networking. There's no abstraction in there. There's no flexibility in there. There's no open interfaces in there. It's all proprietary stuff and has nothing to do with what SDN originally is and what OpenFlow is. So what is OpenFlow? I already mentioned it started in the Stanford University. And over the time, there has been set up a foundation, a group, which is called the Open Network Foundation. And the interesting thing is, I can smile. The interesting thing is, look at the founding members. Some of the founding members are listed here. Of course, we are part of the network, but we came later, I need to admit. So we were no founding members. But companies like Google, Microsoft, Yahoo, Facebook, Deutsche Telekom, you see, those are the big ones. The founder of this foundation, they were the big internet companies because they have the highest need and for flexible networks, and they have the highest use for it. And as I mentioned before, Google, for example, is already using software and a software-defined network, an open flow network worldwide. So Google has two networks. One is the customer-facing network, and one is a kind of an internal network where they do data replication between data centers, they push their indexes through and all that stuff. And this internal network and parts of the customer-facing network also is completely running on OpenFlow with own hardware they designed for it, with an own controller, so it's nothing you can buy in a shop right now. They made it for their own, but it's based on OpenFlow. So what does OpenFlow? OpenFlow, you know, OpenFlow is just this single part here. The connection between the controller and the hardware. To send commands, you know, we talked about that control plane, which is now centralized, which is isolated. This control plane has to talk to the data plane. And the language it uses to talk to the data plane, to set the status of the data plane, that's OpenFlow. And you have a lot of definitions in there. You have, for example, switches that support OpenFlow only. You have what you find more and more. Most of the networking vendors introducing OpenFlow today, they are following a hybrid model, like we do. So you have a switch that even does not have to be enabled completely for OpenFlow. In our gear, you can just enable some single ports for OpenFlow, and then you can have another part of the switch running on legacy technology. So it makes it easier to migrate a technology like OpenFlow into your existing network. You can leave parts of the network as they are, and for parts of the network, you can just introduce OpenFlow. So what we have here is a controller. Then we have flow entries, flow tables, and here, for example, an emergency flow table which can be used once the connection to the controller has been lost. The table entry is rather simple. There's just some rules in there. There's the action that the controller wants the switch to perform, and there's some statistic data. So what happens is, for example, that a packet is entering the controller, and the controller says, okay, this is a packet that has to be switched on layer 2 from this port of the network to another port of the network. So it already knows the whole topology, and it sees where the flow should be. And what it's doing then is just making flow entries. In this case then, based on layer 2. It says, if the destination Ethernet MAC address is like this, put it to this port. That's the whole flow entry. So it's not rocket science, it's rather simple. That's what I already mentioned here. Because you get the presentation afterwards, I put some stuff in there you can read maybe. I don't think we have to go like all the modifying actions you can take. So this is just for you to read afterwards. So let us show at an example. Let's have a look on how that works. We have a simple network here containing of 3 switches, yeah, and one OpenFlow controller. So what happens is, first of all, the OpenFlow controller is sending out an LLDP request to the switches to do a kind of discovery of the topology, discovery of the network. So the switches, they send an LLDP reply. And then the controller knows how the network is does look like. Let's assume now we have two clients. We have client A here on the left-hand side, and we have client B on the right-hand side, and A wants to talk to B. So what does A? He wants to send an IP packet over to B. So the first thing it does is an ARP request. It sends an ARP request to the switch it is connected to. The switch now, instead of flooding it all over the network as we know it from today, is sending this ARP request to the controller. The controller replicates the ARP request and sends it out on all the other switches. So the controller is doing the flooding, which we normally do by just sending a broadcast in a layer 2 domain. And then the ARP request reaches client B. Client B answers with an ARP reply. Okay. The ARP reply doesn't go to client A, it goes to the controller. And at that point, the controller knows where is the source and where is the destination in my network. And it now knows where the flow has to be. So what it does is it adds the flow on the whole way between A and B. And then it replicates the ARP reply it got from client B and sends it to client A. And now client A knows what is the destination MAC address of client B. And from this point on, the flow is established, like we know it today, and an IP packet can be sent from A to B. That's how it works. That's how a flow is established in an open flow network. Come on. Here you see how far we are at the moment with the development of open flow and software-defined network. We started with first discussions with Big Switch, which is one of the first companies having a commercial controller being ready as a product. You can buy it as of today, so you can buy an open flow network today. And we are now here that in January, or it was 10th of February, we brought out version 15.3 of Exos, which is the first general availability version that supports open flow. So since beginning of February this year, you are able to go out and buy an open flow capable network just in the shop. So, and the idea behind is that we once come into a situation like this. We have the classic hardware. We have maybe even virtual switches that rely in servers or other gear. Then we have the controller platform, and we have the applications on top. Which models of our gear at the moment do support open flow? It's mainly the newer ones, like those Summits here. So Summit is all our stackable devices, and we have the Black Diamond, the chassis series. They will support open flow in 15.4, which is planned for maybe in about 4 months. So from summer on, the whole product line, which you can buy as of today, will be able to support open flow. Let me talk 1 minute. So that's the marketing part now. We come to an advertisement. You've seen the Black Diamond X8. Just wanted to show you what it is. It is our flagship. It's the biggest switch we have. It has 192 ports of 40 gig or 768 ports of 10 gig in one 14 rack unit chassis. So in one standard rack, you can implement 576 40 gig or more than 2,300 10 gig ports. And that's what, and the very interesting thing is it just uses about 5 watt per 10 gig port, so the port density is very high, energy efficiency is very high. That's what our flagship is as of today. We have 10 gig ports here, we have 40 gig ports here, 12 port, 24 port, and we are introducing also in summer time frame the first module for 100 gig. And that was the advertisement part. So this is a network you could set up with, let's say, Black Diamond X8 and an open flow controller. And if you have all your services on top here, you already know. It's a multi-tenant capable network, the topology. You have different services there, different users there, they cannot see each other. And this is another advantage you have when you use software-defined networking. You do no longer need things like network access control lists in your switches. As we have seen it with client A and client B, the controller defines whether client A is able to see client B. The controller defines if a packet from client E is accepted at all. So I don't need edge network access control anymore, because the edge port is just asking the controller, is this packet allowed or not? And that's it. So we have all the intelligence of the network in one central place, which is the controller. The interesting thing is that you can use it on any topology. It removes all the limitations you have with standard technologies like VLANs as we have them today. We can have dynamic end-to-end provisioning for virtual machines, for clients, for users using different devices. It doesn't matter. And in terms of if you have the right hardware, it scales up very high. So you can have hundreds of thousands or even millions of flows in one chipset. So SDN may become a viable alternative to what we are doing today. And there are some myths around and legends around SDN, and I just want to mention a few of them. First, SDN is something that is just viable in research environments. It's true that the first SDN and open flow networks, they have been at universities. But right now, you can have commercial versions of those, and you can go out and buy your own open flow capable network. Another point is SDN is not open flow. I think I mentioned that before. And SDN, open flow, it can't scale. I already mentioned Google is running their internal backbone completely on open flow. It's a worldwide network. I think it's, if it would be a service provider, it's number 2 or 3 in the world. So this is a really big network completely running on open flow. It does scale. And let's have a look at where we are right now in terms of the innovation circle. I don't know if you ever have seen this curve. That's how technology innovation normally takes place. There's an idea at the beginning, then there's a lot of expectations and interest about it. Then the first product comes out, which has a limited set of features, which is maybe where we are right now with SDN and OpenFlow. So the first versions that come out now, they do not support all the commands and all the matching conditions and a limited set of flow entries, but it's evolving. And within maybe just a few months even, that's the interesting thing on SDN, the innovation cycle for a new application, for new capabilities is rather short because it's just done in software. You don't have to touch the hardware anymore. And that's where we are today. So the idea behind is that we are going to face something similar we have been seeing at the mainframe, getting into an open area of operating systems. Like phone systems, we now have Android and iOS and that stuff. So the idea is that we get such an open environment and open operating systems and flexibility also for networking gear, which we don't have today. It's still proprietary, it's closed systems, and they have to open up, and then we have the choice and the flexibility to use whatever operating systems we like. So let's have a look at the future, what may come out at this point, and let me talk a little bit also about what will happen to existing switching vendors. So the idea is that open flow, not really open flow, but let's say the the idea behind OpenFlow and the software-defined network becomes a kind of Android we are facing right now for mobile phones. And I've seen now there is the first camera coming out with Android on it. We need the controllers. That's one of the biggest issues we have right now. So the first question you should have is, okay, I have a centralized controller. What happens when a link breaks? And the controller has to modify, let's say, millions of flows. Does it scale? Has it the right performance? What about redundancy? So, of course, the controller is not just one single machine. It may be a cluster. It may be between different locations. You can have redundant controllers. So this is something that happens in reality as of today. And then what you sometimes hear is, okay, now we have OpenFlow. Now we do not need powerful switches anymore. We just go out, buy cheap silicon, and then we are done. So that's not true. Let me give you an analogy. If you have something like this enabled in your car, so you're sitting in your car, and your car has a high level of abstraction, and you can talk to your car. You don't have to touch any button or anything, you just talk to your car. So your car is driving, and you tell your car, go 250 kilometers an hour. And the car is intelligent, so there is the virtualization level, and it knows, 250 kilometers an hour means full throttle. And then there's the network operating system, which knows, okay, full throttle means fuel injection highest amount. Yeah, that's what happens in the technology below. And then you have a 4-cylinder, 1.4-liter engine with 90 horsepower. It will never be able to go 250 kilometers an hour, although it could understand the command. But the capability is not there. You need the big block, the 8-cylinder engine down there, to follow the command accordingly. So you still need powerful switching ASICs. You still need powerful switches. And that's what we are building today, and that's what we are building in the future as well. Thank you very much.